Hello and welcome back to Math 1324. We are in Chapter 7 and we are doing Section 7.4, Permutations and Combinations. Before we can discuss those, we need to talk about factorials and some definitions. What is n factorial? That's this right here. It's an exclamation point after n, and it does not mean n. I'm just kidding. Okay, n factorial means n times n minus 1 times n minus 2 all the way down to 3 times 2 times 1. Now, we also have to define 0 factorial to be 1. Okay, another way we can write n factorial, we can peel off the first term, n, and then all of this is just n minus 1 factorial. That's going to come into play here in a minute. Let's go do a few examples. What is 5 factorial? Well, it's 5 times 4 times 3 times 2 times 1. All right, on our calculator, we can go do 5 times 4 times 3 times 2 times 1, or watch this trick. If you hit 5 and then math and all the way over here to probability, so arrow to the right, and then number 4 is the factorial button. So type number 4 and hit enter. 5 factorial is 120. Okay, what is 8 factorial over 6 factorial? Okay, I can do 8 times 7 times, watch this trick, 6 factorial over 6 factorial, and those would cancel. So that would just be 8 times 7, which is 56. Now, if you're not comfortable doing it that way, on the calculator, I'm going to go do a fraction, and I'm going to do 8 factorial over 6 factorial, which is 56. All right, what is 2 factorial? Well, it's 2 times 1, which is 2. What is 10 factorial? Okay, I'm not going to write that out. I'm just going to go straight to my calculator and type in 10 factorial, which is, ooh, that's a big number. 3,628,000. 3,628,800. Okay, something I want to make note of. Factorials grow very, very quickly. You saw that 5 factorial was 120, and yet 10 factorial is up to 3.6 million. Factorials grow fast. All right, number 5. I'm going to give you a second to go do that. Okay, if you wanted to clean it up by hand a little bit first, 20 times 19 times 18 times 17 factorial. And I stopped there because I saw the 17 factorial in the denominator. And then I also have 3 factorial, which is 3 times 2 times 1. The 17 factorials are gone. 3 times 2 is 6. 6 goes into 18. Whoops. 6 will go into 18 3 times. So I really have 20 times 19 times 3. Well, that's 19 times 60, which is, see, 6 and 5 would be 1,140. Or I can go do my calculator and do 20 factorial over 3 factorial times 17 factorial. And I get 1,140. Okay, over to the right, I saved the screen. Remember, you're going to hit math and then arrow over to probability, and number 4 is the factorial button. Now that we know a little bit about factorials, we can go talk about things called permutations. And I have put in parentheses, order matters. And watch this, when I draw a P, do you see that O sitting up on top? There's an O there because order matters. O, order matters. Okay, definition, the permutation of a set of objects. A permutation of a set of distinct objects is an arrangement of the objects in a specific order without repetition. So an example, suppose that 4 pictures are to be arranged from left to right on one wall of an art gallery. How many permutations, in other words, how many ordered arrangements, are possible? So, going from left to right, we could pick one of the 4 paintings to go on the far left. Now, on the next spot on the wall, there's only 3 paintings to choose from. So now we've used 2 of them, and on the next spot, there's only 2 to choose from, and then there's only 1 painting left. So what is 4 times 3 times 2 times 1? Well, that would be 24. Same thing as 4 factorial, right? All right, there's a theorem. You shouldn't see that. Okay, there's a theorem that says the number of permutations of n distinct objects without repetition, and that's denoted by, okay, look at the notation. The permutation of n, pick n. You have n objects and you need to pick all n. The number of permutations of n distinct objects without repetition is n factorial. That's if you use all n objects. Up here, we had 4 pictures to choose from, and we wanted to arrange all 4 of them in a row. And we found out that that was just 4 factorial, correct? All right, what if we don't want to pick all n objects? A permutation of a set of n distinct objects taken r at a time without repetition is an arrangement of r of the n objects in a specific order. That's what that means. You've got n to choose from, but you only want to pick r of them. And here's the theorem on how to find that number. The number of permutations of n distinct objects taken r at a time without replacement. Okay, look at the notation. Permutation of n choose r. The number n goes on the left. That's the total number of objects, right? Total number. And the r is on the right, and that's how many you want to pick. That's how many you want to take. Okay, you do that by doing n times n minus 1 times n minus 2, all the way till you get to the number n minus r plus 1. Now, usually, we don't see it written that way. We see it written like this. It's equal to n factorial over n minus r factorial. All right, an example. Now suppose the art gallery decides to only use 2 of the 4 available paintings, and they will be arranged on the wall from left to right. How many ordered arrangements are possible? Okay, going from the theorem right up above, we want to do the permutation. We had 4 paintings, but we only want to choose 2 of them. And that's going to equal 4 factorial over 4 minus 2 factorial. Well, that's 4 factorial over 2 factorial. That's 4 times 3 times 2 factorial over 2 factorial. And what is 4 times 3? I get 12. There's 12 ways to do that. Okay, another trick on the calculator. We could type 4 factorial over 2 or we could do 4 minus 2 factorial. We could do it that way. Or we can say there's 4 objects, math, probability. Do you see number 2 says NPR? Hit enter, and then 2. It does it for us. All right, another example. Given the set of elements A, B, and C, how many permutations are possible for this set of 3 objects taken 2 at a time? Okay, I want to kind of pull some things and put them all together. If we used a tree diagram, do you see that the first choice could be any of the 3? You could choose A, you could choose B, or you could choose C. Now, on your second choice, if you chose A, you could either choose B or C on your second choice. On your first choice, if you chose B, then your second choice, you'd be left with either A or C. And so on with the first choice of being C, on the second choice, you could pick A or B. So the different permutations, you could do A and then B, you could do A and then C, you could do B and then A, you could do B and then C, you could do C and then A, and last but not least, you could do C and then B. So how many different permutations are there over here? 1, 2, 3, 4, 5. There's 6. Okay, what if we wanted to use the multiplication principle? And actually, that shouldn't be there. You only want to do 2 choices. The first choice, you have 3 to choose from. And on the second choice, you've already used one of them, so you would only have 2 remaining to pick from. And what is 3 times 2? It is 6. All right, now, what if we use the permutation formula? We have 3 objects, and we want to choose 2 of them. The permutation of 3 choose 2, I did it over here on my calculator, is 6. Example number 2, find the number of permutations of 30 objects taken 4 at a time. So we're going to do the permutation of 30 objects 4 at a time. On our calculator, 30, math, probability, permutation, taken 4 at a time. I get 657,720. Number 3, a talk show will include 4 women and 3 men as panelists. Part A says, in how many ways can the panelists be seated in a row of 7 chairs? So using the multiplication principle, we have 7 chairs, and we have 4 women and 3 men, so there's 7 to choose from. 6, 5, 4, 3, 2, 1. Or we could do the permutation of 7 people, choose 7. So we could do it as 7 factorial, or we can do 7 permutation, pick 7. 5,040. On both of them, we get 5,040. Okay, choice B says, in how many ways can the panelists be seated if the women and men are to be alternated? Okay, let's do looking at the seats. 1, 2, 3, 4, 5, 6, 7. All right, they have to be alternating. We've got 4 women and 3 men, so we need to start with women, right? We have 4 to pick from. So we're going to do 4, 3, 2, 1 women to choose from. And for the men, we have 3, so we can choose 3, 2, 1. Now, if we do that on our calculator, 4 times 3 times 3 times 3 times 3 times 2 times 2 times 1 times 1, we get 144. Now, another way we can think about that is the permutation of 4 women. Pick 4, you want to select 4 of them, and then permutation of 3 men, and you want to choose all 3 of them. So on our calculator, 4, pick 4 times 3, pick 3. I get 144. Part C. In how many ways can the panelists be seated if the men must sit together and the women must sit together? Okay, we can think about this as the men and then the women, or we could think of it as the women and then the men, right? So this was men and then women, women and then men. All right. So for the women, we had 4. 4, 3, 2, 1. 4, 3, 2, 1. And for the men, we only had 3 to choose from. All right. Now, we want to add those together because we can set them men first and then women, or we could set them women first and then men. If we do this, 3 times 2 times 1 times 4 times 3 times 2 times 1, we get 144. We get 144 here, and we also get 144 here. So my answer would be 288. Now, if we want to think about it in terms of permutations, this is, what was that? Permutation of 3 pick 3 times permutation of 4 pick 4, permutation of 4 pick 4, permutation of 3 pick 3. Again, we get 288. Number 4, in a horse race with 8 horses, in how many ways can the horses finish first, second, and third? Okay, do you see why order matters? They finish. You can actually order these first, second, and third. There are 8 horses, so we can have 8, 7, 6. I have 333 different possible ways. Now, I put the first, second, third down here because that indicates order matters. And remember, order is with a permutation. 8 pick 3, 8 pick 3 is 336. I'm trying to show you that there's 2 different ways to think about this. I tend to think about using the multiplication principle. All right, number 5. A teacher has 5 books and wants to display 3 of them side by side on a shelf. How many arrangements of 3 books are possible? Okay, again, order does matter because you want a first book, a second book, and a third book. There's 5 to choose from, so what is 5 times 4 times 3? 5 times 4 is 20, times 3 is 60. Now, since the order does matter, we can do the permutation of 5, choose 3. So 5 math probability permutation, choose 3. I get 60. Okay, now let's go talk about combinations. And notice up here I wrote order does not matter next to combination. When you write a C for combination, it doesn't connect. There's no way to make that into an O for order. So remember that order does not matter. There's no order. Okay, the definition: a combination of a set of n distinct objects taken R at a time without repetition is an R element subset of the set of n objects. The arrangement of the elements in the subset, subset, does not matter. All right, an example. In how many ways can 2 paintings be selected out of 3 paintings? Remember this one above? We said there's 3 choices to choose from for the first painting, and then each one left, you had 2 choices. So we ended up with 6 permutations. Now, if order does not matter, if we did A and then B, that would be the same as doing B and then A, because A and B are both up there. It does not matter what order they're in. All right, so let's get rid of all the doubles. AB, BA, AC, CA, BC, CB. All right, so there's only 3 different combinations of 3 objects taken 2 at a time. Does that make sense? There's 6 permutations, but only 3 combinations. All right, theorem. Number of combinations of n objects taken R at a time. Okay, some books will use this notation, and that's what's on the calculator. I'm pretty sure that's what's in our book. That's what I'm going to use. Sometimes you'll see it written stacked on top of each other in parentheses. Sometimes you'll see it as the permutation of n pick R over R factorial. And sometimes they'll just give you the formula n factorial over R factorial times n minus R factorial. All right, some examples. From a committee of 12 people, in how many ways can we choose a chairperson, a vice president, a secretary, and a treasurer? Do you see that those have labels? Assuming that one person cannot hold more than one position. Okay, so we have a chairperson, a vice president, a secretary, and a treasurer. So chair, a vice president, a secretary, and a treasurer. Those have labels. So order will matter. And we have 12 people to choose from, and so on. Okay, since the order matters, that is a permutation, permutation of 12 people, pick 4. Okay, on my calculator, 12 times 11 times 10 times 9. Oop, times 9. All right, or I could do 12 permutation, pick 4. 11,880. Okay, do you see a difference in that question and the following question? In how many ways can we choose a subcommittee of 4 people? You have 12 people, you just want to pick 4 of them. You're not giving titles to those 4 people. So the order does not matter. You're going to have the combination of 12, pick 4. 12, math, probability. Do you see number 3 is the combination? Pick 4 at a time. 495. Okay, how many ways can 4 patients be assigned to 6 hospital rooms so that, yes, you've got 6 hospital rooms and you need to pick 4. Let's read that one more time. In how many ways can 4 patients be assigned to 6 hospital rooms so that each patient has a private room? Okay, the order will matter because you've got these 6 rooms. We're going to call it room A, B, C, D, E, and F. You've got 4 people to choose from. Order will matter, so we're going to do the permutation of 6, pick 4. And I get 360. All right, number 3. And how many different samples of 3 light bulbs can be selected from a batch of 15 light bulbs? Okay, we're not labeling any. We just want to get a sample of 3 from a batch of 15. There's no order, so we're going to do the combination of 15, pick 3. $455. Okay, now we're going to go talk about some applications. Believe it or not, there are some students that do not know what a standard 52 card deck is. So before we can go talk about cards, we need to talk about a standard 52 card deck. It consists of 4 suits. You have hearts. Hold on. You have hearts. You have spades. You have diamonds. And you have clubs. Now, in each suit, you have the following cards: ace, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then you have your face cards. Sorry about that. Jack, queen, and king. So again, Jack, Queen, and King, these 3 are called face cards because they have little faces on them instead of just numbers. All right, so let's go ask some questions. How many 5-card hands have 3 aces and 2 kings? 3 aces and 2 kings. Order is not going to matter. So to find out how many aces, we've got the combination. There's 4 aces to pick from, right? 1 from each suit. And you want to pick 3 of them. And you want 2 kings. Well, there's 4 kings to pick from, and you want to pick 2 of them. All right, so 4 combination pick 3 times 4 combination pick 2. 24. Now again, we want 5 cards, right? We're picking 3 there and 2 here. That means we're picking 5 cards total. All right, number 2. How many 3-card hands have all cards from the same suit? All right, from one suit, there's 13 cards, and you want to pick a 3-card hand? So let's just talk about the hearts. You want to pick 3 cards from those 13 cards. But you can do that with all 4 suits. So you're going to need to multiply this by 4. So 4 times the combination of 13, pick 3, is 1144. All right. How many 5-card hands have all face cards? How many face cards are there? Remember that? From each suit, we've got the Jack, Queen, and King from each suit. So there's 3, 6, 9, 12. face cards. There's 12 face cards, and how many do you want? You want 5. So the combination of 12 pick 5 is 792. How many 5-card hands have exactly 2 hearts? So how do you get exactly 2 hearts? How many hearts are there? There's 13 hearts, and you want to pick 2. Combination of 13, pick 2. That's how you get exactly 2 hearts. All right? But you've got to pick 3 more cards because you've got a 5-card hand. So how many cards are not hearts? Well, if 13 are, and there's 52 total, 52 minus 13 would be 39. So you've got 39 cards to choose from that are not hearts, and you want to pick 2 of them. So 13 combination, pick 2, times 39 combination, pick 3. And I get 712,842. Now, one more time. There were 13 hearts. You wanted to pick exactly 2. There were 39. Oh, shoot. There were 39 non-hearts, and you need a 5-card hand, so you need to pick 3. Scratch that. Just kidding. This is exactly 3 non-hearts. Oh, I did that here. I just wrote it down wrong. That is the right answer. Okay, number 5. How many 5-card hands have all cards from a single suit? Combination. There's 13 cards in a suit, and you want to pick 5 of them. But that's just for the hearts. You've got 4 different suits to do that from. So what is 4 times the combination of 13, pick 5? 5148. Number 6. 2 jurors are selected, one at a time without replacement, from a panel with 1 Hispanic, 3 Caucasians, and 2 African Americans. In how many ways can 1 Caucasian and 1 African American be selected? Okay, let's go talk about the Caucasian first. You want to pick 1 Caucasian out of 3. That's going to be the combination of 3, pick 1. Now, you want to pick 1 African American out of the 2. That's going to be the combination of 2, pick 1. Combination of 3, pick 1, times the combination of 2, pick 1, is 6. Number 7, from a group of 15 people, 4 are to be selected. There are no labels to these 4 people. There's just 4 people. So it's going to be a combination. How many ways can this be done? Combination, 15 people, pick 4. $1,365. One of the people in the group must be Bob. How many ways can the 4 people be selected if Bob must be among the 4 that are selected? All right, so there's a combination of one Bob, and you want to pick one of them. Now, how many members are left? 14? And you need to pick 3 of them. The combination of 1 pick 1 times the combination of, what was it, 14 pick 3. 364. Number 8. How many 5-card hands are a full house? In other words, 3 of a kind and 2 of a kind. All right. How many ways can we get 3 of a kind? So of a kind, you have like 4 10s, 4 2s. So there's 4 cards that are the same kind, and you need to pick 3 of them. But there's 13 different suits to do that with. There's ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, king. Okay. Now, you also want to get a 2 of a kind. Oops, not a plus. You need a 2 of a kind. So there are 4 cards that are all the same name. So they're all 3s or they're all 7s. And you want to pick 2 of them. But you've already got 1 suit accounted for, 1 set of numbers accounted for. So there's only going to be 12 remaining for the 2 of a kind. So let's see what we get. 13 suits, and there are 4, and you need to choose, what was it, 3 of a kind? Yeah, 3. You also are going to have 12 left, and you need to pick 2 of a kind. So you're going to have 4 combination 2. I get 3,744. All right, I believe this is the last problem. A club has 7 senior and 5 junior officers. In how many ways can a 4-person committee be formed if any 4 officers can be chosen? So you have, what is that, 12 to pick from, and you want 4? That's going to be the combination of 12, pick 4. $495. Okay, what if there must be 4 senior officers? Okay, there's 7 senior, and you've got to pick 4 of them, so that's going to be the combination of 7, pick 4. I get 35 different ways. All right. What if you must have 3 seniors and 1 junior? Okay, how many ways can you do 3 seniors? Remember, there's 7 seniors to choose from, and you want to pick 3 of them. So it's going to be the combination of 7, choose 3. Now you want to pick 1 junior officer, and you had 5 to choose from. So the combination of 5, choose 1, 7, choose 3, times 5, choose 1, and I get 175. All right. Are there more? Yep. Okay, what if 2 must be senior? Now I've got to remember there were 7 seniors and 5 juniors. All right, 2 must be seniors, so the combination of 7, pick 2. and 2 must be juniors. Combination of 5, pick 2. 7 combination, pick 2, times 5 combination, pick 2 is 210. Okay, what if there must be at least 2 senior officers? All right, this gets a little tricky. At least 2 senior officers. So there could be 2 senior officers, there could be 3 senior officers, or there could be 4 senior officers, right? Okay, the way to get 2 senior officers, you're going to do the combination of 7, pick 2, and then the remaining 2 are going to be juniors. So you've got 5, choose 2. Now for 3 seniors, you're going to have 7, pick 3, but you still got to have a 4th person. So you're going to do combination of 5, choose 1. That's how many juniors there are, pick 1. And then last but not least, if you wanted 4 seniors, there's 7 to pick from, and choose 4 of them. All right, typing all that in. 7, 2 times 5, pick 2. Okay, 7, pick 2 times 5, pick 2, plus, all right, 7, pick 3 times 5, pick 1, and then one more. 7, pick 3, 5, pick 1, plus 7, pick all 4. 420. Again, this is 2 senior, 2 junior, 3 senior, 1 junior, 4 senior, no juniors. And that's it. All right, now it's time to go practice. I encourage you to go log in and do the homework. Until next time, bye-bye.